our world and beyond. Space, in partnership with the European Space Agency.
Gravity is one of the fundamental forces of nature. Its invisible grip governing our planet, from the rocks inside to the seas on the surface. And that makes it a vital reference point.
Gravity gives you the feeling of downwards. So what you call down is surely the direction of gravity.
We feel gravity as a constant pull, but add in extra mass in one spot or take it away, and the gravity signal alters a small but measurable amount. It's a puzzle for science.
Since more than 10 years, I would say since 20 years, scientists were dreaming of having a mission which gives us a high-resolution gravity field.
Gravity can vary in different ways. It can vary over time because of movements in mass, and it can vary from place to place.
In reality, we have different densities, different material in our planet, which is reflected by dips and bumps in the gravity signal.
In fact, if you look at Earth with the gravity-scanning eyes of a satellite, it looks a very strange shape indeed. "300 years after Isaac Newton observed an apple fall from a tree, the students near Trieste in northern Italy are getting to grips with gravity. This is a fascinating starting point because beneath the ground is a huge cave called the Grotta Gigante. The cave's presence means the force of gravity here is slightly reduced.
The Grotta Gigante cave is a mass loss because it's a big hole below our feet, and this gives us a nice gravity signal.
Less rock beneath your feet means less attraction towards the Earth. But the cave isn't the only factor in the local gravity field.
We have made 3 measurements in half an hour. And the student asked, yeah, but why do I see a gravity change? I'm sitting in the same place. So the answer is it's changing because we have earth tides. So the action of moon and sun changes the gravity field, and the Earth responds elastically to the changes in gravity and deforms.
The best way to get a global picture of the gravity field is to go to space, and ESA's GOCE mission does just that. Developing this unique global picture offers geologists an unprecedented view inside our planet. By studying GOCE's gravity data, experts like Carla Breitenberg can track the structure and history of Earth.
This is a sedimentary rock, is a fossil included. This has smaller density. If we take a magmatic rock, this is a basalt, you feel it's much heavier. And this is typical of a volcanic environment. The third rock, which I brought, is a metamorphic rock. That means one or the other has been brought to very high temperature and pressure. The rock got cooked, and you get an even higher density. And this kind of rock type we want to detect by looking at the GOCE measurements.
That gravity information can lead geologists to valuable materials like iron ore. It can also reveal how the roots of mountain ranges reach deep into the crust.
The crustal thickness variation is by about 7 kilometers in the ocean. They're the thinnest to about 70, 75 kilometers over high mountains like Andes and Tibet.
Measuring the force of gravity can also tell us a great deal about the oceans. The waters of the seas are attracted by gravity towards concentrations of mass in the Earth's crust. Those same waters are also moved around by currents and tides. The goal is to understand the relationship between those two.
The mass distribution in our Earth, which determines our gravity field, is constant compared to the time an ocean current moves. So constant means over many years, over many decades, 100 years, 1,000 years. Whereas ocean currents flow. And if we know, as I said already, the gravity field, then we can see the effect of the ocean currents, which is about 40 to 80 centimeters on top of the gravity undulations. And this we want to measure. This the oceanographers need for the climate models.
The streams of data on the gravity field from the GOCE satellite land here at the European Space Agency's Esrin base near Rome. The team that handles that information are aiming to make even better data available to the scientific community, and that means flying low.
We are currently in a phase of lowering the GOCE orbit to bring it as close as possible to the Earth's surface, and thus to increase the sensitivity of the instrument for the Earth's gravitational field.
GOCE has always flown far lower than other satellites, but now it's dipping down to an altitude of just 237 kilometers. At that height, the satellite is bumping along the outer edge of our atmosphere.
It can get quite wild depending on the sun activity, but at that low altitude, air drag becomes an important player for what concerns, let's say, the influence on the satellite's orbit. So that's why we have an ion drive on board GOCE, which compensates the air drag that is impacting on the satellite.
One of the ultimate goals of GOCE is to improve our knowledge of the geoid, a kind of gravity map of the planet. That strange, misshapen and theoretical view of Earth has long been studied here at Potsdam, home to the GFZ German Research Center for Geosciences. Since 1995, scientists here have sent satellites into space to measure gravity. But way back in 1892, they were watching the gravity field here using a very precise pendulum in a room with a heated floor and temperature controlling valves.
The story is that we have a pendulum which is swinging roughly with a period of 1 second and a length of 1 meter in a vacuum chamber, and you can derive from the length and from the swing period the value of gravity very, very precisely. And that was the reference value which we used for nearly 70 years in the last century. Nowadays, we are using satellite systems like the GRACE mission. GRACE stands for Gravity Recovery and Climate Experiment, and what we are observing are tiny changes of the distance between the two satellites, while the first satellite is pulled to a mass in the system Earth, while the second satellite does not observe that at this moment.
The pair of GRACE satellites don't have the high precision of other missions, but they do offer something unique, and that's a monthly survey of the gravity field. Ingo Sasken has been using that temporal data to track the loss of ice mass over Greenland in the past decade.
You can see two things. So one thing is that you can see a seasonal cycle, but you can also see within the period of nearly 10 years, the bluish colors start to dominate, which means that the ice sheet has much less mass than we had before. Gravity is a very accurate and very true recorder of the mass change. And I think if you see these images here, there's no doubt that Greenland ice sheet loses mass, and we can accurately quantify it.
So, measuring the direction and force of the Earth's gravity field from space can allow us to follow not only changes in climate, but also see deep down through the crust into the mantle.
The big innovation of GOCE is that for the first time we can have a global field which has the precision and resolution which is good enough to see mass changes which are related to geological structure.
Tracking the geoid, that gravity map of the planet, is also crucial for untangling complex questions in surveying and navigation.
That is very important because this surface is our reference surface which defines us what is top, what is bottom, what is the reference for defining heights. For example, if you want to know the height of the Himalayan, you measure the distance between the mean sea surface level and the mountains.
All branches of earth science have a healthy appetite for gravity information.
There's never an end in science. So, of course, we look ahead. We also discuss, for example, with our NASA colleagues whether we make a joint mission, because also NASA is working on the gravity field to determine the ice mass at the poles very accurately. And we are discussing whether we make a joint mission which takes the best of the two concepts to improve the gravity field further in the future.
Gravity will eventually be the downfall of GOCE as its orbit is left to decay at the end of its mission and it re-enters the atmosphere. Its legacy is an unprecedented global survey of gravity's grip on Earth.